The open source, it's open source, but they're like research projects. Like,
Oh, that's pretty cool.
yeah, this one.
These are pretty cool.
So then you can say anything. And to
Firefox.
Don't question it.
Yeah, it just does the thing.
Okay. Can somebody please check the live stream on their phone to make sure we haven't screwed anything up? We've screwed something up. I'll find a way. I'll make sure none of this.
No.
Is that?
But if it was, well, no, maybe it is. I just ripped it off the internet. I'm live, right?
Yes.
Yeah.
Your sins
I'm a pirate. I'm a pirate.
Sins are being broadcast. Is that creative?
Yeah, I put the Creative Commons filter on.
Yeah, so it's currently just feeding staring off into space and a black screen.
Oh, okay. Is it not seeing the full screen? Oh, okay. I will window capture then. It's probably. Firefox.
Nice.
But the camera's not working.
Oh, has the camera shut?
Such a well-organized society.
Please tell me the camera.
Oh wait, it's working now.
Yeah, it just freezes every time.
Is this the camera or OBS? Well, we don't know.
Who knows?
Who knows? Okay,
we're live.
That is stable.
Merry Christmas.
If I freeze, then it's fine. I'll just be frozen. I mean, it's the way it is. It's part of the performance. Exactly. All right, am I good to go? All right, are we good? All right, sweet. Thank you for coming. I know it's week 4 and you're probably getting busy, maybe, I don't know. I'm having fun. I'm not teaching this semester, so everything's good for me. Yeah, so thanks for inviting me to do this talk. Basically, I'm going to tell you a little bit about how kind of a large-scale web search engine works. That'll be the main focus. So, for example, Google, Bing, these types of things. You're all pretty young. Do people still use web search engines? Some of you do, maybe? Yeah, okay, good. Yeah, you're directly accessing the information. I'm not that sophisticated, but yeah, so yeah, hopefully I'll be able to teach you something. I've kind of tried to keep the level. Hopefully there's something here for everyone, but we'll see how we go. So firstly, just a bit about me. I've been working on search engines for about 10 years now. So I started my PhD in 2016. So yeah, been working on this stuff for about 10 years. Before Brisbane, I was in Melbourne for basically from when I started my undergrad to when I finished my postdoc. So I was at RMIT and then at Melbourne Uni. And then in 2022, I managed to get a job here. I actually showed the 4X gold can in my job interview. This is actually the slide I had. The VB wasn't there though, the 4X was. Since then, I've been a lecturer for a couple of years and I've just started a fellowship this year and I've just become a senior lecturer as well. So I've been, I think, yeah, UQ since 22 and I've taught since second sem 22. So you've probably seen me around. Just to give you a sense about people I work with and companies and stuff like that, maybe it's interesting, maybe not, but there's a bunch of people around the world who I collaborate with on search-related problems. The information retrieval is the sort of discipline. It's a pretty big community. And so some of the companies in the middle are like next-gen startups for AI, basically. Instead of people searching, AI agents need to search. So, and then you've got some, I guess, old school stuff like Amazon, maybe old school now, or Microsoft. But in any case, lots of really smart people work in this field, and it's lots of fun. So this is just a quick journey through some of the stuff I've worked on. Something that's not always super clear to people is that there are an extremely large amount of things you can do in information retrieval. There are users, there are systems, there are algorithms, there's modeling. So there's a whole lot of stuff you can do. This was the first paper I ever published, and this was about when you run queries like best cafe near me. So you want you want basically location awareness. You don't want recommendations of things that are far away from you. You want things that are nearby. So how do you essentially optimize your performance in terms of latency and quality for these types of problems? There's a lot of niche stuff here, so I won't talk about it all. This one's a little bit interesting because this was work I did at an internship at Microsoft, and this was about understanding how people interact with the Outlook search. Everyone hates Outlook search. Sorry, Microsoft people. And at the time, this is when they were rolling out the thing. If you've ever used the web Outlook, there's this panel at the top that's like 3 top ranked results and then the date ranked results. And we were trying to understand if people actually liked relevance ranking in email. Yeah, people hate it. So this is what that paper's about. People essentially hate it. The best results are nearly always at the top, but people can't find them because they're so used to using dates to find what they're looking for. Most of my work's been stuff like this. You may recognize some of these words, but basically about making things fast. Sometimes it's about understanding what people do as well. So this is sort of understanding how people insert queries to search engines. So these are some of my less hinged, I suppose, titles of papers. Some data compression stuff. More recently into the LLM stuff like everyone else. And so just to give you a little sense about the sort of things that come out, this is my research, but it's sort of pretty good representation of the field as well. You get these clusters. So the green clusters like the performance stuff, indexing, data compression, data structures, algorithms, how do you serve billions of documents fast. The blue stuff at the top is kind of generic to the field. So people have intent, they want to find something, they issue a query to a search engine, so they're kind of like generic terms. And then on the right is a thing that I guess a lot of people don't really think about. It's how does the ranking work when you interact with a search engine? How do you make sure the good stuff goes to the top? How do you make sure that people get information that's, I guess, relevant to what they're looking for, but also perhaps factually correct, not letting spammy stuff get up to the top and that sort of stuff as well. So obviously you all kind of know what search engines are, but the kind of point that we want to make is that we're not necessarily trying to generate answers to questions. That can be part of it. But what we're doing is we're looking at all of the stuff that's out there that we can find. We're indexing the web basically. And we're trying to give you shortcuts into stuff that you might be interested in, right? So we're not necessarily trying to give you the answer immediately. We're just trying to point you to stuff that's interesting. It's kind of like lecturers. We don't teach you everything you need to know. We kind of just tell you what to look for. Nowadays, though, you would understand, and you've seen this, that a lot of search engines do generate direct responses. So if you ask a question, it will often generate an AI answer. Often it's right, sometimes it's wrong. And users, us, we interact via text or voice interfaces, often with very short and uninformative queries, right? So think about the last time you searched, you probably punched a 1 or 2 word query and then hoped that the magic search engine would find the stuff you're looking for. So you can kind of think about it like this. Maybe I'm in Melbourne and I'm interested in finding some coffee shops, so I type best coffee in Melbourne. It's not bad. I get a kind of 10 blue links is what we called it. So you get, this list of 10 things, and very few of you ever click to the second page. Most of you look at the first 3 things, and if there's nothing there that you like, you type a new query and try again. Sometimes you disappear forever. But this is a very clean example. Actually, this is more likely what happens. Like, people just don't care. They just type, they don't think. Sometimes you get a little, did you mean this? I'm showing you answers for this. And sometimes the results are absolutely not at all what you're looking for, right? And I'm sure you've all experienced this before. So we're going to dive into some of these ideas today. Because I mostly work on efficiency, I'm going to mostly talk about efficiency, but I'm very happy to be interrupted. So if you have any questions along the way, let me know. But I'll mostly talk about sort of the way the systems and the data structures inside are built and how they work. But I'll also have a little bit of time to talk about modeling, ranking, and other things if you're interested. So why do we need search to be fast? Well, you're all very used to receiving a response in about half a second, right? Like, if you type a query and press enter and you wait about that much, you're probably refreshing. Am I wrong? I mean, I do. I'm super impatient. And so the problem we have is that we would like to return really high quality stuff, but we also have this time bound that we essentially can't get away from. Users are very impatient. They're gonna wait maybe 1 or 2 seconds most. And so returning good results quickly is much more important than returning the best possible results slowly. Like, we can't wait a minute or two. Actually, that is changing a little bit now with the new sort of agentic search stuff, where you can say, hey, plan me a 2-week holiday to Japan, and I want to go here and I want to go there. And you're happy to let it sit there and spin for 5 or so minutes and dump you out a nice big 10-page plan. But typically, if you're on web search, you're interested in things really quickly. These guys know what they're talking about. Jeff Dean is the chief scientist of Google and DeepMind, and Luis Barroso was kind of a pioneer of modern data centers. Google were one of the first search engine companies to admit that all of their indexes were being served out of RAM. So back really early on, even when RAM was quite expensive, Google came out with a paper and said, everything we do is in memory. We don't serve any indexes on disk if we can help it. And that's why they were so fast, right? And of course, with that, there were challenges such as redesigning the way that data centers laid out, the servers you use, things like that. So the way that you might think about it is, if you've got this, so 0 on the left there is sort of when you press enter on a query. If the results come back and they're pretty good and they come back faster than a user expects, they might be happy or excited or glad. And then you've got this middle ground where it's kind of what you expected. The results came back, you didn't care, you use the search engine, life goes on. And then the 2-second plus on the right is you starting to get pissed off because you don't want to wait. No one wants to wait for anything anymore. You start refreshing, you type a different query, you try Bing instead, right? No one ever did that, but anyway. So what actually happens though is it's more like this. No one cares if it's fast. As long as it feels fast, no one actually cares if it's faster than 200 milliseconds, 500 milliseconds, 1 second, whatever. If it's fast, it's good. If it's slow, it's really bad. But if it's really slow often enough, people actually leave and never come back. And I told you a little lie a second ago. There was actually this study in 2009, where Google and Bing both, they injected artificial latencies into their search engines, and they observed user behavior. So when the results were ready for presentation, they would hold them back for an extra 100 milliseconds or 200 milliseconds or 500 milliseconds, and then they'd release them. And you blink, it takes you about 400 milliseconds to blink your eyes. So it's not really a delay that people should perceive. But they found that as they increased the delays, user engagement started to decrease, and some of the users actually left and didn't come back. They went and found a different search engine, and they stopped using the product. So this stuff is actually measurable and super important. The other facet of this that's kind of interesting is the resource consumption. So because it's easy to generate content, we're all monkeys on typewriters, and now we have AI to do that as well. The amount of data being stored on disks is basically exponentially increasing. It's something like more than 50% of the data on hard drives in the world, including phones and stuff, was generated in the last couple of years. So, that's pretty nuts. And if it's on the internet, if it's on the web, we're kind of expected to be able to give you the answers from those things. Even if they're super obscure, maybe things that no one actually looks at, they're out there, we should be able to retrieve them if they're relevant. This is what a Google data center actually looks like, at least pre-AI. So these are CPU-based racks. Just as a point of interest, when you submit a query, not an easy one, so there are some easy queries and hard ones. An easy one's like Brisbane weather tomorrow. That query comes in thousands of times a day, mostly from us, people in Brisbane, or people coming to Brisbane. They're easy. But maybe there's a hard query, like someone's trying to find some obscure thing that they saw 2 years ago. It's got weird words that don't occur very often. How many servers do you think that your query actually goes through? You press enter and about half a second later you get results. How many servers do you think your query's touching? Any guesses? Yeah, 5,000 or so would be. Yeah, so your query is going off to Sydney to a data center, and it's being routed into a bunch of different servers that have little fragments of different bits of the web indexed. They're all being searched, and then the results are kind of being sent back to another program that's making decisions on what to show. So there's tons of this hardware being used to do search. And what that means is that search is very expensive from a resource perspective. Electricity costs are very high, and carbon costs are very high. This was actually so this paper was in 2019. This was pre-LLMs, so this is when we had transformers. So if any of you have worked on like NLP stuff, you might have heard of BERT. BERT now is kind of pretty small and a little bit old, not really, but it hasn't been around for that long, but it's kind of outdated now. It's sort of a precursor to GPT. You can think of it in that simple term. This large transformer LM they're talking about here, this is training it. This is the amount of pounds, so they're Americans, sorry about that, pounds of CO2 that were emitted for various activities. So New York to San Francisco return flight is like a couple of thousand pounds of CO2. Training BERT on a large snippet of the web to kind of get reasonable performance was something like 1 million pounds of CO2, right? So now we've gone probably magnitudes above that again with the GPTs. So just the point is it's very expensive to do this sort of work, right? So our challenge for the web search engine provider is you need to return the right answers to hundreds of thousands of probably bad queries every second. So Google gets about 120,000 queries a second, so forever. These collections, the web contains billions of documents, petabytes worth of data, right? And you have to do all of them in about under 200 or 500 milliseconds, and you have to keep doing that forever. Who's up for it? Yeah, come and see me. Yeah, we can do this together. All right, so I'll talk a little bit about the system architecture now, and then I'll go a bit more into the data structures and algorithm stuff. Hopefully it's interesting. Like I said, if anything's confusing, let me know. So the World Wide Web is just a bunch of web pages with links that point to each other. It's a big graph. You know, it's colorful points that look cool. I made that figure 10 years ago. I think it's cool. So what you have is a crawler. The crawler basically, the job of the crawler is to go out there and find stuff it hasn't seen before or updates to things it has seen. So perhaps every day or so, the UQ web page, the crawler will come and say, hey, has anything on this page changed? And if so, ship the page back so that I can process it and update it, right? Of course, every day there are new pages. You're all updating UQCS's website, you know, Instagram, whatever. So new stuff's appearing all the time. You have to go out and find it. When you find it, you bring it back into a document store, and then you have an indexer, and the indexer's job is just to look at the documents and basically make them searchable fast. Okay, the index is just the data structure that helps you find stuff quickly. On the other end, user queries are coming into the user interface. They're essentially being propagated through to a query engine that knows where the indexes are and what's on them, and it goes and processes the queries, finds the results, and gives them back. Now, it's easy to think that there's one search engine, so Google is one system. It's actually hundreds of systems. So, for example, we're talking today mostly about the web pipeline, the large-scale web search, but you've also got probably an image search engine. You've got a question answering pipeline. You might have an ads, well, you will have an ads pipeline in this day and age. If you're serving ads, you will have an ads pipeline. There will be a social media one. There might be a news feed one. These are all actually different search engines. They could use the same underlying system. They could be different. They could be bespoke to the task. And so when your query arrives, the first thing actually that happens before routing is that they try and understand what you're asking. So they're trying to predict the intent of your query. So if you say something like best cafes near me, they don't really care probably about image or maybe social media. Well, maybe social media is a good one for that because people might be talking about cafes that are good or so on. But you know what I mean, maybe news is less relevant. But you could also think of cases where news could be relevant, like best espresso roaster competition or something. So basically the idea is that they try and figure out what you're interested in, and then they try and route your query to the right places. Sometimes it's all of the places. All of those little individual search engines send their responses back. And of course, each one, like I said, could be thousands of individual search engines on their own servers with little chunks. All of that stuff comes back. The SERP is the search engine results page. It's the thing you see. There's also a team responsible for how they order things on that page. Where does the ad go? Do we put images first, or do we put the summary first? Do we AI generate or not? All these types of things that change every time you issue a new query. they kind of, all the bits come together at the end, right? And so here's a query, LV bling shit. So the interesting thing here is Google has decided, and note that I'm logged in, so they definitely have personalization on me. They know stuff about who I am, what I do, for sure, right? So they go, well, he never swears, so he's obviously looking for a shirt, right? But they're very surprised because I'm not very stylish, so they don't know why I'm looking at LV. But anyway, they've decided here that I'm looking for shopping stuff, right? So they've served me products. This has come from like an ad or a product search engine. And look across the top, images, and then shopping, and then videos, and then shorts, and then news, right? So even that top bar has been ranked. It will change order depending on what I ask, right? You may not notice, but you might from now on. They've decided that my query was wrong. They've tried to rewrite it for me. And you can see that they've really pushed these ads. They think I'm shopping, right? If I ask the same query for Bing, Bing believes that I swear. They're not trying to rewrite my query at all. And they're actually trying to serve me things that I'm asking for, which apparently is a talking chip music video and Louis Vuitton is tacky and ugly, unpopular opinion, Reddit. I didn't say that. But you can see that it's totally different, right? And at the top, you've still got shopping coming before images here. So they perhaps know that when I ask about LV, I'm asking about shopping. I'm sure I'm being put in a filter right now. And you can see as well, searches you might like. So that's another part of the search engine that you probably don't think about very often, but they're saying, well, people that search for LV bling are also usually searching for LV wallets or LV Australia. They know where I am, right? So all of this is happening behind the scenes. For the web part, like I said, I've kind of already pointed this out, but because the web's so big, it's like petabytes or exabytes worth of data on disks. You can't possibly search it all. So what we do is we split it up into chunks. There's kind of head content, torso content, and tail content. Head content is stuff that gets accessed all the time. People go to Google and search Facebook because they don't want to type Facebook in the URL bar. They just Google it and then click the first link. So these are head queries. They happen all the time. They're the most repeated queries. Then torso queries are things that are seen less often, but still often enough. So perhaps like UQ Bachelor of Science academic advising. You know, that's not a super rare query, but it's rare enough to be a little different to the most popular ones. And then tail content is like when you try and find some weird YouTube video you saw 10 years ago and you can't remember the words, so you type like a 20-word query with quotes that you can't quite remember and no results come back. They're really hard queries, generally. And so often the content is sort of prioritized into tiers. I won't go into much detail about this, but most of the head content, the stuff that gets found often, it'll be on really fast, in memory, really fast servers, kind of really high up in the search stack, so you can find it really quickly. And then the tail content, the websites that haven't been served in a results page for 10 years, they're probably on a really slow system that doesn't get accessed very often. So you can kind of, because you can see what people are accessing, you can kind of sort it out in a way that's easy to deal with. So under the hood, with the ranking part, it kind of works as a multi-stage system. This is a nice sort of, if you're into system design, you might be kind of a little bit interested in this part. So when the query comes in, we route it to these servers, but all the servers are doing, the part I'll talk about today mostly is called candidate generation. The job is just to find things that are probably relevant. It doesn't have to even be ranked really well. It's just find me a big bunch of stuff that I can use to answer the query, right? So it's not the answer, it's just like a set of stuff that's probably useful. And this is kind of one of the big jobs the search engine has. After you do, and so there are two techniques. I'll talk about both, mostly sparse. So the data structure inside is called an inverted index. This is like a token-based matching thing. Like if you give me the words cat, dog, it's trying to say which documents have cat and dog in them, for example. So it's just like word matching. There's also these vector indexes, which are kind of like vibes-based. I'll talk about this a bit at the end, but you may have noticed more recently that when you type a query, you get results that don't actually have any of the words you typed in them, but things that are kind of related, like it can read your mind. That's the vibes-based dense indexing stuff. In any case, you do candidate generation. The point of that is to kind of, you just get the big grey box is just find some stuff that's probably useful. After that, you pass all of those probably useful things onto another set of algorithms, and they essentially re-rank and filter that big initial set of results. And so this re-ranking stage might use features that are computed offline. For example, the web URL that the page came from, Wikipedia, for example, is probably quite useful because people like it, it's reputable and so on, but maybe like my personal website is bad because no one goes there. So there are like these features you can pre-compute. You essentially pass all of those documents in and some magic algorithm will re-rank and filter them. And that's actually what gets shown to the users, right? And so this is called re-ranking. Back in the day, we used gradient boosted decision or regression trees. Maybe some of you have learned about them before. But basically just feature-based learning to rank, feature-based machine learning algorithms. Nowadays, we tend to use transformers, so like GPT style things inside here. Of course, we're trying to keep them cheap where possible because it's really expensive to run LLM generations. So from a systems perspective, you start at the bottom and you have this multi-stage pipeline. So at the bottom, you're just saying, give me a bunch of stuff, maybe 100 million things, maybe 10 million, maybe 1 million, but lots of stuff that's probably useful, surface it from the web. Then as you go up the pyramid, you're saying, okay, this stuff's bad, throw it away. This stuff looks pretty good, maybe re-rank it, chop, re-rank again. And so what it looks like is kind of this process where you get this big list of things and then more and more expensive models start to like tweak the ordering and then chop. And then a more expensive model will come along and take the green input, it'll chop some off and then it will flip the ordering of what's left and so on, right? And there could be 4 or 5 or 6 stages. Does anyone have any idea why we do this? Like why don't we just use the guy at the top who's really, obviously really good at ranking? Why don't we just let it rank everything? Yeah, cost, because it would take 1 million years to run every query. So at the very top of this thing, you might be re-ranking like 20 things to decide which 10 make it on the first page, or you might be re-ranking the top 5 things to decide what's at the top, right? Interestingly, human attention on search engines is essentially like this. You pay, like I said earlier, most attention on the first thing, a little bit of attention on the second, a little bit less on the third. And as you go to the second page, the attention drops. So it's like a staircase that goes like this because no one goes to the second page. And if they do, they spend even less attention on the things going down and then even less, right? So it's really important to get good stuff at the top. And so we know that users are really sensitive to latency and we don't want this thing to cost heaps. So how do we stay within our time budget? This is starting to sound like corporate tech speak stuff, but has anyone ever heard of service level agreements? I hadn't until I started doing research. So this is like an agreement that a company essentially makes with a consumer that says, for example, maybe you want to use an API. It'll say like 99.9% of the time the API will be up. We're allowed to be not up 0.1% of the time, right? Or we'll give you your money back. They don't really say that, but that's meant to be the idea. So we actually apply this to search engines. Think about the pyramid as like a team. There's a team responsible for the candidate generation. There's a team responsible for the indexing. There's a team responsible for the first level re-ranker. They're all kind of individual teams who focus on their component. So each team is given a budget. The people doing candidate generation might be told that 99% of your queries have to answer within 100 milliseconds or less. So that's what P99 means. It means the 99th percentile latency over all time has to be under 100 milliseconds. And then the next team might be told, okay, you get 50 milliseconds. So 99 and 100 of your things have to be done in 50, 45, and 30. Can anyone think of why we do it like this? It's a little probability trick. If someone at the bottom level is the 1 in 100 that is outside of 100 milliseconds, right? Took 150. What's the probability that they will also be above the 50 in the second stage? Yeah, the probabilities multiply as you go up, right? So basically what we're trying to do is make sure that if something really bad happens here or something really bad happens here, it's very unlikely to happen there and there as well, right? So overall, you're kind of getting a reasonable average experience. Okay, that was my motivation. I'm actually at the point where I can talk about something a bit more concrete. So we're going to talk about candidate generation today, and just to give you the problem again, you're given some query Q. Q is like a set. It's a set of words. Best coffee Melbourne. Why do UQCS keep inviting me? I don't know. And what we want to do is find some list of K documents. K is big, 1,000, 10,000, 100,000. And you're going to pass those K things on to some more sophisticated re-ranking algorithms. You can think of it as some magic AI BS. It doesn't actually matter. It's very interesting, but I don't have time to talk about it today. I'm happy to talk about it after. So what we do is build an index. So imagine we have 3 documents in our giant web collection. The first one is search is cool. The second one is search is fun. And the third one is search is fun for everyone. I'm not very imaginative, sorry. These IDs are coming from the order I see documents. So if a new document appeared, I'll just say, well, it's the next one. I'll call it 3. And then another one appears, I'll call it 4. You just start labeling off from 0 up. Now what you do is essentially for each document, you walk across the words in the document. And if you haven't come across them before, you store them in a dictionary or a lexicon. It says, hey, I found a new word. Okay, so look, I found a new word. I've never seen search before. Here it is. And then you kick these things called postings lists. Now, these are just lists that are telling us which documents have the words in them and how many times the words occurred, or some other payload, right? So, search occurred in document 0 once. You might decide, so there's a couple of techniques you can do to cut down on index size. In English, there are some very common words, is, of, and, the, so on. And they occur in almost every document. So maybe they're not very useful. In fact, you would index them, but you just might not use them at query time. But this is called stopping, so we might just skip them. I came across a new word, cool. Okay, put it in my lexicon. It occurs in document 0 once, and so on, right? This is literally it. This is all you have to do to build a global web scale search engine, okay? And then that's what an index looks like. But of course, instead of having 3 documents, you have like 100 million or more, right? Does that kind of make sense? Do you see how we're going to use this thing? This is called an inverted index, by the way. The reason it's called an inverted index is because maybe the most intuitive thing you'd think is, if I get a document, all I need to know is which words are in it, right? I don't need to care about I kind of took the documents and turned them on their side in some way, right? Because I'm mapping for each word, which documents have the word, rather than the document being, this is a document and these are the words inside. But if I didn't do that inversion process, every time I wanted to answer a query, I'd have to look at every single document to check if the words are in there, right? So that's why I do this inverted indexing. So we've got document identifiers. They're like tuples, right? They're pairs. The first thing in the pair are the document identifiers. The second thing are the term frequencies. This is a very boring one, but the ones could be 2s or 3s. So there could be a document on UQ that has UQ in it 50 times. So that would be 50, not 1, right? It's just keeping how many times I saw the word. Each is a pair. Document 2 contains the word fun once. That's what that means. Okay, and I'll show you how to use this in a sec. Now, one interesting thing to note is because we labeled the documents in order that we saw them, we know that those document identifiers have to be strictly increasing, right? Because the lists always get bigger. So 0, 1, 2, 5, 8, 15, but the numbers can't go down, they can only go up, right? Okay, let's search the index. So what we do now is we've got kind of this thing sitting in memory. It can be on disk as well, but most of us use memory now. So a user will come along and enter a query. The first thing we need to do is see if we've seen those words before, right? And if we've done any pre-processing on the words, for example, what we would always do is we would reduce uppercase to lowercase. Because if someone puts UQ in capitals or UQ in lowercase, they're still probably looking for the same thing. So we don't want to miss out, right, if someone uses something different. Another thing we do, which I won't talk about very much, is called stemming. A query like cat or cats, both are related to the same concept. So we slice off the S. We fold all of the cats into cat and then we index them together, okay? So user puts the query in, we normalize them according to the same recipe we used for indexing, and then we can look up those lists and use them to answer the query. So in this query, we're gonna have Best Coffee Melbourne because it was the example I used all the time 10 years ago, and it's stuck in my mind. So the other thing I've done here is I've thrown away the second part of the postings list. So these are not pairs anymore, they're just identifiers. Because this is a Boolean conjunction, I don't care about how many times the word appears. All I want to find is the set of documents that have best and coffee and Melbourne, have to have all three, okay? So we basically have what's called a cursor. It's going to be like an iterator across each postings list. Now, the first one, best, is pointing at document 12. That's the first document that has best in it in this example. Now, why am I doing this? So what is my query again? I want to find the documents that have all three words, right? So the first document, if you just look at the example and don't think too hard, the first document that could possibly have all three words has to be 12. Because 8 couldn't have it, because if 8 was possibly an answer, it would have to be the first thing in the first list, right? So 8 can't be an answer. So we already know that the maximum of the three things under the cursors is the next candidate I'm interested in. So I'm looking for 12. So I walk up and say, I found 12 here. Okay, Melbourne's on 2, so let's see. Oh, I found 12. Oh, good, look, all three cursors point at document 12. I found a document that has all three words. It's really simple, isn't it? Is it? I think so. I mean, I think that any of you could hack this up in 20 minutes, maybe, yeah?
I'm just thinking like large scale. Let's say you have like 1 billion documents.
Yep.
Like doing a forward walk on this would be...
Yeah, it's a great intuition. So the point is, hey, like when you're doing these walks up, and I'll keep going through the example, you see all these little movements going up, trying to align things basically. If these lists are going to be really long, which they are, right? So a normal index shard maybe has 50 million docs or something. So like 50 or 100 million documents, you would be able to get your latency in the 20s of milliseconds per query. So yeah, you're going to have 50 million things here, worst case. This is going to be slow if you do it like this. This is not exactly what you do. I'll kind of hint at that a bit after. So good intuition. We found another match here, by the way. We found 55. And at the instant that any of these cursors walks off the end of the list, I can stop, because to answer the query, I have to have all three words, right? So I can immediately stop now. And I had two answers. I had 12 and 55. So the intuition is that because these things are sorted, I can kind of scan all the lists together. It's like a multi-way merge, basically. You can do disjunctions as well. You could answer any... So for example, you might have a query that says you have to have 2 of the 3 words, or any of the individual words would be sufficient. And it's the same sort of thing. Instead of finding the max, you find the min next thing, and so on. So the kind of intuition's the same. What I ignored totally from this conjunction was ranking. So what if I want to actually say, I want to return the top 10 things I think are best? How do I do that? I don't have enough time, sorry. But I'll give you some intuition. So if we're talking about counting words in documents, term frequency, that corresponds to the number of times a word occurs in a document. What do you think that means for ranking stuff, intuitively? More is better, right? So the more times a document says dog, probably the more likely that document is about dogs, right? But we don't want that to actually be linear. We want it to be like a logarithmic scale, because if you think about it, it would be really easy to make your document always the best one. You just put every word as many times as you can in the document, and it magically always goes to number 1, right? So we sort of smooth it off. Another idea is inverse document frequency. So there's an inverse there. Document frequency is the number of documents that have a word in it. So what does that mean? How many documents have the word the in them in English? Probably nearly all of them, right? Most of them. So is it an informative word? No. How many English documents have yeetus in them? Definitely not all of them. Most of them. No. So the point is that the less a word occurs, the more impactful it should be. Like the rarer a term, the more impactful it should be in ranking. To an extent, if you're only seeing a word once or twice, it's probably a typo. So there's like this sweet spot in the middle. Things that occur really often, not useful at all. Things that occur super rare, probably sketchy to use them. Things that occur kind of in a sweet spot in the middle, probably quite useful, right? So UQ is obviously a very useful term. UQCS as well, probably. And the last thing we need to think about is that if I want to beat you in a ranking, well, I can just make my document really long, put more words in it, right? So what we have to do is we kind of have to normalize. Documents on the web are of all sorts of different lengths. So we need to kind of have a normalization that says short documents won't be penalized because they're short, and long documents won't have an advantage because they're long, right? And so there was this algorithm called, or like a ranking function called BM25 that uses these statistical properties. And this was actually engineered in like the 80s or 90s. It's still used today, which is crazy. So it's quite interesting. This is sort of the best baseline algorithm you can use today. Even if you're building a search engine on data you know nothing about, you basically reach for this first. Something built in the 80s, which is really cool. This is what it looks like. Scary math, not really too bad. Basically, it just says for each query term that the user puts in, this part here is the number of documents in the collection. So say I have 100 million documents, that's big N, divided by df of t is the number of documents that have that word in it. So this part is the inverse document frequency. This is basically boosting rare words and penalizing common words. And then the stuff over here is just how many times does this particular document I'm trying to score have that word in it. Like if it occurs lots, then good, it gets a bigger score. If not, very often the score's a bit lower. And then this is the part that's normalizing long and short documents to kind of put them in the same space, right? So it looks kind of freaky, but it's pretty simple. Everything you need is actually stored in the index already. So the term frequency part over here comes from the postings, right? We already index, so we know how many times each word occurs. The df is actually how many postings are in each list. So search occurred 3 times here. It's in 3 documents, right? K1 and B are random parameters that you have to tune out of thin air, and no one knows how to tune them, but there are some defaults that seem to work reasonably okay that everyone just uses. Okay, so you just ignore those. And then this is like the average length of a document in the corpus, and this is the length of your document. So if you've got a long document, you'll be penalized. If you've got a short document, you'll have a weight increase, right? Okay, so in practice, I sort of getting to the more interesting stuff maybe. You can't really just walk across lists of millions of things, right? If you enumerate every element, I mean, it's hard to build a mental model of this, but even if you're at home and you write some Python code, like make a sorted list in Python with like 10 million things in it, and then walk across it and sum them up or something. It'll take like some milliseconds. It won't be super slow, it won't take like 2 minutes, but it won't be like 1 millisecond either. It'll take some time. So how do we actually do this? Well, the first thing that we need to worry about is storage. We can't necessarily store all of this stuff uncompressed. It's just going to be too big, right? Think of every word in every document, counting them, turning them into integers. Each integer is 32 or 64 bits. You've got millions of those in each list. It's going to be hundreds of gigabytes index. Suddenly it won't fit in RAM, right? And by the way, RAM is big. Like in a production server that you might use, like the one I run experiments on that's in my office, which you will forget about after I said this because I don't want you thieving my hardware, has 500 gigs of RAM. So that's normal, right? 500 gigabytes of RAM, not disk, 20 or 30 terabytes of disk. So we're trying to keep our indexes in sort of up to 100 gigs maybe, right? So smaller. So we need to compress this stuff. An easy thing you can do is because, hey, you know those doc IDs always increase, right? You just take the differences. It's called delta coding. So I had a 12 and a 14, the difference is 2. So instead of 14, I put 2 here. And then I have a 27, and I had a 14 before, and the difference there is, I hope 13, it's probably not because I'm bad at arithmetic, but I'm taking differences. Now, the interesting thing here is if I want to figure out what document has a word in it, now I have to do a prefix sum. So I have to start at the start. To decode this 13, I have to do 12 plus 2 plus 13, right? And then the next document's plus 2, plus 2, plus 25. So I'm taking the sum from the start up to the position I'm interested in. Now, come back for a second and think about it. What if that list has 1 million things or 1 billion things? And you want to find the second last doc ID? You're going to have to go to the start and sum everything up to that point. That's going to be really bad. So what you do instead is you actually break into fixed size blocks, about 128 elements. You keep the first one of each block in its undelta, uncompressed form, and then you only have to do prefix sums from the start of each block. Do you kind of get what I'm saying? So instead of having a giant list of differences, you just take the difference relative to the first thing in each individual block, and to decode any element, you just have to go to the first thing in the block and then take the prefix sum up to anything in that block, right? Does anyone know why I actually wanted to make those numbers smaller? Like if everything fits in a 64-bit integer or something, or a 32-bit unsigned, why do I care about making the numbers smaller? Any ideas? Yeah? I like that. This is like a kind of canned response to anything I talk about. People know I love bit vectors. No, you're on the right track though. When you build these blocks, you actually then compress the blocks as well. So you don't just take the deltas, you then put them into a compression codec, and that block of stuff turns into a binary mess that you don't know what it is until you unpack it and look at it, right? So everything's compressed. Anytime you want to access something, you need to go and get that block, decompress it into a buffer, take the prefix sum, and now you can look at anything inside, right? So blocks are typically quite small, about 128 things in each block. And you interleave these in memory for better locality, because when you're accessing document identifiers, you probably want to access the frequencies that correspond to those documents. More than likely, you want them at the same time. So if you put them near each other in memory, you won't have cache missing very often when you're actually running through and processing your queries. Hopefully that makes a little bit of sense to some of you. There's a bunch of compression codecs. So some of them started early as 49. 2019 is when this paper that has these in them was written. There are more today, so people love compression, it's fun. One interesting thing though is this is the distribution of those gaps. So remember I said you take a number and you look at the next one, you take the difference and you store the difference. This is the distribution of the gap sizes in real English collections. What this means is that most of the time you get really small gaps, runs of ones, right? So that feels kind of weird. That means that like in an uncompressed list, you've got like 101, 102, 103, 104, 105. Why would that happen? It's a sort of weird answer. You might not think about it. It's not super intuitive, yeah?
Is it that the scripters are adding documents from similar sources at a similar time?
Brilliant.
Similar doc IDs?
Absolutely, exactly. Because the crawler goes and says, hey, I'm going to go and look at UQ now. What's on every UQ page? Queensland, University, UQ, purple. And so what you get is all 2067, I don't know how many pages UQ has, something big, they're all in a run, right? Queensland has those documents in the list all next to each other. They're all ones. Ones are very easy to compress, life's good, right? What you don't want is really giant gaps because they're harder to compress, the numbers are bigger. But it turns out that the web is kind of well behaved, which is nice. The other interesting thing about compression, which I'm not going to go into, but it's always a trade-off. Smaller is slower, almost always, right? So you want fewer bits per integer, you're going to pay in query processing time. If you're happy to compress less, then you can go faster, okay? It's always a trade-off. Oops. Do you think it's charged enough? Okay, I'll keep it off. I'm getting excited now. So the other thing that's interesting is I was talking about this. Most of these collections would fit in 32 bits. They would have less than 2 to the 32 documents. But these compression codecs are good enough to get you down to about 5 or 6 bits per integer, right? So you're saving about 5 times on uncompressed. So if your uncompressed index is 100 gigs, you've got like a 20 gig index in memory. Okay, so that's nice. The other thing that we do is we use very complicated algorithms that avoid work. I won't go into detail. It's really quite complicated and you're going to have to think about it pretty hard. But the intuition is that because you've got everything in blocks, there are ways to decide which blocks you don't need to look at, and you can skip over them. So you've got all these compressed blocks. At some point in time, you can say, hey, nothing in these blocks is interesting to the user. Don't look at them. Just go directly to something further on, and you skip across them. And so avoiding decompressing those blocks and avoiding computing those scores, like that complicated function I showed you earlier, is how we make query processing faster. This is what one of the algorithms looks like. 40 lines of pseudocode, not too bad, but a little bit complicated, lots of stuff going on under the hood. So how fast is fast? I'm getting to the end here, so I think timing's pretty good. This is real experiments. So I told you I have a beast of a server in my office, has, some thread rippers, got 500 gigs of RAM. I put everything in memory. I have this 52 million document index, and I want to run some experiments. That's about 2 terabytes of raw text, just the text itself. So you index the 2T of text. Who wants to guess what the index size turns out to be? Just take a guess. Everything you need to run queries fast and rank them, give the top K answers to the users. How much index do you need for 2 terabytes of docs?
50 gigabytes.
50, yeah, not a bad guess. Yeah, about 20 or 30. So yeah, that's pretty good. So it might be about 20 or 30 in compressed form, so you can load that 20 gigs into memory and start asking queries. Imagine that I'm going to return the top 1,000 things. So when you come to my crappy search engine in my office, you can say UQCS fun or something, I don't know. You want 1,000 answers returned, okay? So the naive algorithm is going to look at every single posting in all of those lists. It's going to decompress every block. It's going to look at every individual thing, score every single document, and return the best K, right? So it's essentially an exhaustive algorithm. If you had to guess how long it takes, I'm asking you for a per query average or something, and queries have about 2 or 3 words on average, okay? So they're pretty short. Just guess, how long do you think it takes the naive algorithm to do this? Average query. Per query? No, that's good. That's a good guess. No, it's actually not so bad. 150 milliseconds. If you build your index right, you get the good compression codecs, you engineer things properly. The only thing not engineered here is the query processing algorithm itself. Everything else is kind of at blazing speed, right? P99 means that 99% of the queries I ran completed in under about 1.4 seconds. But remember, my job isn't to get the top 1,000 things that might be interesting, it's to get the top 100,000 things, right? So 1.4 seconds is not going to be anywhere near good enough for a web search engine like Google. 150 milliseconds in the median, not so bad, right? So what if I use those fancy algorithms and all the tricks I know, and this is the stuff I've been working on for 10 years. If I throw everything I have at this, what can I do? How quick? Guesses? 50. And what do you think? Do you think on the average? So I've gone a three times improvement on the median. What do you think about the 99th percentile? So like the hard ones, basically. 3 times as well, so maybe like 500 milliseconds. Okay. 9.7 in the median, and 80.3 at the 99th percentile on the same set of queries, right? And by the way, this was done in 2020, so these are old results now. Now that is probably getting close to good enough for a real search engine, right? Because a real search engine is really a giant server that has about 50 million documents per index. So maybe you're getting close enough to be reasonable. I was going to show a demo, but I'm not on my computer. Can we? Yeah. Let me do this first. I'll do the what I didn't talk about, and then we can do the demo last. So I could talk about this stuff forever. It's quite interesting to me. The reason I got into this field was because I wanted to make software fast. I liked algorithms, I liked systems, I wanted something that was at the intersection. But search is actually such a big field. There's a lot of moving parts. There's a lot of really interesting stuff that make a web search engine successful. So, this is really how I type. I'm very poor at typing. Maybe you can't see it. It's riddled with typos, but somehow Google still knows exactly what I'm looking for, right? So this whole thing that you see, this auto-suggestion, that's a team or a bunch of teams. There's a team that work on the data structures that make it fast. There's a team that work on how to rank the suggestions to you, right? Yep, so I don't know the answer to any of these, by the way. The other thing is I talked about just one little part of one bigger system in the whole scheme of search engines, but there's all this other filtering and re-ranking that go on after my part, right? So what do they look like? Well, just briefly speaking, a lot of them look like you might imagine you pass the document content to an LLM or something like that that's engineered to be fast and small. And it's seen, you know, the thing that I haven't talked about at all is that these systems have seen so many queries from so many people that they have this incredibly rich data. They know what people want to see. They know which websites people like. They have all this intelligence. So they bake it into their ranking, right? So it's like take the documents, pass them into some fancy machine learning model that's optimized for ranking and is really fast, and it does the job, right? Lots of interesting challenges in there. The other thing I said was nowadays we have this other type of thing going on where, has anyone heard of embeddings before? Any ML people? So embeddings, you can think of it like this. Before we were treating every document as like the individual tokens, right? We were saying we know these words are in the document. Vectors or embeddings instead they have a fixed dimension. So you say, okay, every document is D-dimensionality floating point numbers. So you might have 768 floating point numbers that represent a document. And then to do querying, everything goes into the index and you find the k nearest neighbors to that thing in the D-dimensional space. We can think about 3 dimensions as humans. We can't think about 4 or 5 or 300 or 768, but you can kind of get the idea from this picture. How do you index stuff? It just all gets fed through a model that embeds. It turns your text into a vector, into an embedding, and it puts it in the D-dimensional space. And things that are kind of vibes-based similar to that appear in similar areas. So bananas and apples go together because they're both fruits. Apple, the company, might be near Apple, the fruit, because it's related but kind of not, so it'll be a bit different. And then Google might be near Apple because they're big tech companies. And then way over somewhere else in another part of the space, you might have animals, right? And so this is how that vibes-based stuff works, where you don't actually necessarily match on the exact words, but you match on sort of concepts that we might not even be able to understand, right? Like latent concepts. Of course, everyone's seen this. Now you're getting the AI overview. So this is me. I'm about done. I'm just about to defend why my work is still important now, even though we're all using chat models. Well, to answer questions like this, you go off and you retrieve stuff, right? So you don't just generate from a model because models hallucinate, they're not reliable. So what we do is we give evidence to models and say, here is a set of facts, use the facts to generate an answer that a user might like or engage with, right? And so as part of that, this is called retrieval augmented generation. Retrieval is search, right? So I still have a job, I'm still happy, life's good, okay? All right, there's stuff about users, evaluation. How do you test online? If you ship a new, I don't know, feature, make your search box slightly more white or slightly more green, or you change the size of the search thing in the corner or whatever. How do you know if people like it or not? Push it to prod and see what happens. There's like lots of cool stuff about large-scale testing. So actually what happens is we all get sliced off into little buckets where they test new features on all of us all the time. It's called A/B testing. Yeah, it's A/B testing. And so that's right. And there can be tens of thousands of tests running at once. There probably are, right? So if you're looking for answers, you can come and talk to me now or later. I've got a few UQ plugs. NLP does a little bit about information retrieval. If you're interested in this language knowledge sort of technology stuff, NLP would be interesting. Cloud does a bit of vector databases. If anyone's a master's student, you can do INFS 7410. Super good course, very up to date. They literally teach you stuff that came out in papers like 2 months ago. But it's only accessible to master's students. Very sorry about that. High performance computing if you're interested in the systems and making stuff fast. But most of all, most importantly, learn your data structures and algorithms, and life will be good. Okay, maybe you're just looking for pizza. If that's the case, is it here? Is there pizza? Okay, so we have demo time? Or, okay, we can do a quick demo. No pressure.
We might not actually be running the demo on the live stream then. Yeah.
It's a private demo for the real ones.
Yeah.
Is that okay? Yeah. I was gonna demo some actual like prod stuff as well, but I'll give you the code. Yeah. Yeah.
I'll go. I really hope that hasn't been frozen on live the entire time. Oh well.
No, that's the end, so that's fine.
Cool. Am I good to kill the live stream? Or do we want to keep it running?
Kill the what stream?
The live stream.
Would you like your demo live stream or you don't mind?
I don't mind, but I don't think we can capture it properly, unless you want to try and do the sketchy screen thing.
Okay.
I can actually I'll just record the demo and then I'll just
on the camera
stream.
And then
You know, Premiere Pro fixes everything.
Yeah.
Yeah, I'll cut the stream, then I'll start a recording on this so that you can sync the audio later.
Yeah, cool.
Yep, cool.